This is the OCT pressure device. To use it, first plug in the air compressor, the one with this pressure regulator on the top. This is a positive pressure compressor, and the OCT, as well as putting this down on the table next to the two devices and plugging it in with its power cord right here. You can see everything below. We have power adapters for the OCT pressure device and also for the OCT, and just the cord for the compressor, which I'll plug into the wall. Also, put down the MSI laptop next to the setup and plug it into if it's low on battery, so that you have these four devices set up next to each other on the table. At first, don't power on the air compressor, not until you're ready to test. You can power on the OCT, and you don't need to power this on either just yet. To get started, go to the MSI laptop and open Arduino IDE. It will open automatically to the correct project. If it doesn't, go to File, Open, and find Pressure Encoder in Documents Arduino. And it will be this file right here, the only file in the folder. So we have it loaded. And then to see the serial output from the Arduino, just connect it to the laptop with the USB cable. And then it will connect and give you the output. In the output, you can see all of the diagnostics. So it will tell you if it's read the SD card correctly, which data it has been able to read off of the SD card, and whether or not it was able to connect to the internet and retrieve the date. If it says that there is no SD card inserted, look at the SD card slot, which is behind the motor connection, the motor power connection. You can see this one is a 64 gigabyte Transcend micro SD card. If it is in the port and it still doesn't read, just take it out and put it back in. And if it isn't able to connect to the internet, then to change the Wi-Fi network, just type Wi-Fi into the serial terminal, and then the SSID, a comma, and then the password. Of course, this isn't a real network, but it will save them. And then on the Arduino, press this button directly next to the power connection. This is the reset button. Press this, and it will try to connect to the new Wi-Fi network. Of course, I put in a fake network, so it will not connect. The only information that the Arduino takes from the internet is the date and time. So if it doesn't connect, it will just use a default fallback date and time, which is midnight on January 1st, 2025. So it might be best to make sure that you're connected to a network just in case you need that date to organize your files properly, or just in case it hits the same fallback date multiple times, it will overwrite the old file with the new file because they have the same name. That's not likely to happen because the file, the date in the file name is down to the minute, but just in case. Now, once you're connected, it's also sometimes helpful to open the plotter. So just put this window in the corner for convenience, and then press this in the top right. It's a little picture of a graph line, and it says serial plotter when you hover over it. So just press that, and it will open the plotter window, which will give you a live feed graph of the force and motor position when the program starts running. I like to put these on the right side just so that I can also see the OCT and use them all at once. As with always using the OCT, make sure that it's powered on before you open the program. So just open the blue program here, and sometimes it takes a second, but now we're connected. Hit preview, and then you can just put your finger in front of the OCT to make sure that it's reading properly, and it is. Now, just so that I can see and interact with all of the windows at the same time, I'll cut the right part off of the OCT window and put it on the left here. So now we can use them all. Now, one last good step before you turn the motor on is to just make sure that it's at position 0 Every once in a while, between runs, this will start to creep up because the motor movement isn't perfect because it's 1.8 degrees to a step. So sometimes it's nice to just turn it out, turn it back in, and then as soon as there's a little bit of resistance, you know you're at 0. Once this is all ready, just turn the motor on by giving power to the power supply. And once it's powered on, this green LED next to the power jack will light up. Now, even when it's powered on, you should still be able to move the motor because the motor loses power when it's not being moved. But it's best to do that still when the device is turned off. Now, to run a test, you need to go back to the serial terminal and type load followed by the name of your program. So I wrote one program called default, so I'll just type load default and hit enter, and then it will tell you where it's loaded the program from, which is just in the in folder on the SD card, and then your program name .csv. You can verify that it's loaded by typing list. It won't list the CSV, but it will list the instructions that it's turned the program from the CSV into, which are then run by the program interpreter. This program here, which prints if you type list, is empty by default, so you don't really need to worry about the contents of it, just that it's there. Because if you forgot to load your program, it will not print anything when you type list. So now that you're ready to run a test, just click on the pressure compressor and put the OCT up to your sample and then type run. I'm not going to put anything up to the end of the OCT because I'm filming. But once you're ready to run the program, just type run and then hit enter. The motor will move and you will see data coming out through the serial terminal, also in graph form in the plotter. Now there's no force appearing in the plotter because my finger isn't against the OCT, but I'll put it against it real quick. And you'll see for that last second there when I put my finger against the OCT, the force went up just slightly. Now there's one thing to consider when you're running the trials this way. So if I type list again, you'll see the first instruction says R500, that is the record instruction. So that tells the program how long to record for the CSV data in time based on the number of OCT frames that you're recording. So this default program assumes 500 OCT frames because that's what the OCT program defaults to. But if you're using more or less frames, you should make sure that that number matches what you're using. Now this is also based on the program, so the interpreter will calculate based on your CSV file how long it's set to take in time, and then calculate the number of OCT frames based on the time span from beginning to end. So 500 frames is 20 seconds. One more thing to notice in the list of instructions here is that there's one that says T1000 in the beginning and another one that says that in the end. That's just a 1 second timer that does nothing. And this is to give you some buffer time for the beginning and the end of the OCT trial, because in case you start the OCT and this program at different times, there's a little bit of wiggle room for you to still be able to get the entire motor movement within the OCT recording time. So now I'll do one more trial where I also run the OCT just to demonstrate. I'll turn the compressor back on. And then I like to go over to the serial window and type the word run before I press enter, just so that all I have to do when I run the OCT is come back here and press enter. I'll go over here, I'll click M mode, and then I'll come over here, and as soon as the frame blinks in the OCT window, I'll enter run. This time, I'll put my finger up against the end of the OCT. And you can see the layer of skin falling and then coming back up again as the motor moves. You can also see the force changing in the plotter again. It's just a little bit because the scale is in grams. But you also saw that little bit of a visual defect in the OCT when it got to the last step there, which you can see in the final image. There's a little bit of a blank spot here. That happens when the OCT is up too close to your skin. Because what happens is the pressure will build up in the spot between the end of the OCT and your finger, and it will cause resonance in the skin on your finger, which will vibrate, and that causes the OCT to not be able to read an image there. So the only way to fix that is to just leave a little bit of a hole, hold the OCT at an angle against your skin, and that will keep the image fairly clean. Now, your entire image should look like this bit at the end here with the decreases and the increases, but this one doesn't because I only put my finger onto the OCT halfway through the recording. Now that we're done, I'm going to turn the motor off. You don't have to, but I like to do so just to be safe. So just cut the power to the power supply, and the green light will stay on for just a second, but then it will dim down. And that's how you know that the motor is off. Now at this point, we can also turn everything else off. So the OCT is off, the compressor is off, the motor is off. And I can come over here and close out of this software, and also close out of Arduino IDE. While this is powered on, there's one more thing to note, and that is how to calibrate this and the reason for the gauge being right there at the end of the line. So if you want to make sure that your values are accurate, like after you've changed the input pressure or the pressure sensor, neither of which should happen usually, but in case you have to, disconnect this from the OCT and come over to the laptop here. I'll restart this just so we can watch the startup sequence again. This way, you know that it's powered on and that everything is successful. So with the motor on, turn the compressor on too, and we'll come back over to the laptop, and to run a calibration, just type CAL for calibrate into the serial prompt, just like that, and then when you hit enter, it will give you instructions over the terminal. So it tells you to place your finger at the end of the outlet tube. As you adjust your position of the finger on the tube, you can watch the pressure gauge move, like this. And it will tell you to adjust until you have it at 20 kPa. So once it's there, just type next into the serial terminal and hit enter. And when it's done, it will take 0 points. Make sure that your finger is not on the end of the tube when it does that, because if it is, it will build pressure inside the tube and that will affect the measurements. All of the values for 20 kPa, at least with the current hardware, should be around 1045 and 566 or 567 for the 0 points. When it's done, it will save the file to calibration.csv, which is in the /sys folder on the SD card, and it will be saved even between reboots. So you only need to do this every once in a while if you think that the data is wrong or if you change hardware. You should never need to do this usually. When you're ready to take the data, remove the SD card from underneath the motor power connection. Just slide your finger on the top. It can feel a little bit rough, but actually that is how you're supposed to do it. And take the SD card. Put the SD card into an SD card reader. Any kind of one will do. Just like that, and then this has a USB-C connection. So once you plug the reader into the laptop, you'll be able to read the SD card, and you'll see the 3 folders. One is called out, and this is the one that has the data in it. So these are files from the past 2 days, and the one that we just recorded is this 2025-12-27 14/21/59 OCT.csv. If we open this, you can see the format of the CSV. There are 4 columns. It is time on the left in milliseconds, and then force in grams in the next column to the right, pressure in kilopascals in the second column from the final one on the right, and then motor position in steps in the last column. So I'll repeat. This is time in milliseconds, force in grams, pressure in kPa, and motor position in steps, which is 1.8 degrees per step. Now, once you are fully done taking the data off of the SD card, open up MATLAB and I like to have it all organized into one folder per trial. So this is data from yesterday. I have the OCT images right here on the right, and then I have the CSV file from the SD card, which I've renamed F1110. And now the first one after the F is just your subject number, and then the last three numbers are condition values. So 1 and 1 are constant, and the only thing I was changing was the last value. So in the MATLAB folder, you'll have these 4 MATLAB files, which are the image to CSV, standoff tracking, the Young's modulus calculations, and then the final graph. So open all 4 of these, and inside here, just put your data. So you can see my f1110.csv in the data open folder, and then put in a different folder with the same trial name, but without any letters at the beginning, all of the images generated by the OCT from every folder, just all of the JPEG files in one folder. Now this is 500 slides, so it should go up to 4_100.jpg. I'll open these 4 MATLAB files. And now we have the window open. Make sure that you have the correct numbers in for the file name. So mine is 1110, and then when I run this, you can change the folder to the current working directory. When it's done generating your final compilation image, it will show you. So this is also flipped upside down because it makes using the software easier. But this is the center column of all of the individual OCT images stitched together into one larger OCT image. Now, depending on the tissue that you're measuring, this is just about what the graph should look like. So it should have large spikes upward at the beginning of each round, and then kind of level off near the end as the tissue gets stiffer the more force you apply. So every one of these rounds should look kind of flat. Now, after you run the first script, in the data save folder, there will be 2 files that are generated, i110.csv and i1. Now, after you run the first script, there will be 2 files generated in the data save folder, and that's i_yourtrialname.csv and i_yourtrialname.jpg. And in this case, that's 1110. So just copy the CSV file into data open, and then go to the next script, which is s1 standoff, and make sure to change the file name to the correct one again. So i11 or just 1110, and then run. And now here, you need to start by tracking this straight line at the top. So click on one point on the left and one point on the right, but it's a straight line, so it's easy to track. And then click stop once. And now you need to track this at the bottom, which is the more difficult part. Because these images are so round and sort of detailed, you need to add a lot of points to be able to track them accurately. But tracking them accurately is important for the quality of the data. So every time there's a curve, just add a point. If you have an extended straight line, kind of like these here at the end, just maybe add a point in the middle for accuracy. But overall, make sure it follows the whole curve. Don't leave out any features, because that is all important data. If your curve has a little visual defect in it, kind of like this blank straight line at this point, just kind of go with the averages around and draw the line through it anyway. And then we finish. So once you're done, click stop one more time, just to finalize. You'll see it'll kind of turn the line that follows your dots into a dotted one, and then double click the stop button. And it will give you the final tracking at the top with the standoff, the flat line removed. So this line at the top is just the raw deformation from the force that you applied. After that, go to the next script, which is S2 Young, and again, change the file name to the right one, and then press run. And now this is also tracking, but it's easier because it's just going to find minimums and maximums between the points that you draw. So put 1 point on each side of the leftmost curve, and then 1 point on each side of the one on the right, and it will find the minimums and highlight them in green. And then do the same thing here, but this time for the maximums. And then once you've done that, it will give you the hysteresis loops on the bottom right and the force deformation and time relationship on the bottom left. So once you have these graphs, go back to this one at the top, and then just click 1 point on either side of this flat section, and that's how it will find the original thickness of your tissue. Now, depending on the quality of your data, the hysteresis loops at the bottom right will be more or less resemblant of this kind of shape here. But if it looks a little bit wiggly like this one here, that's not a problem. So finally, we run the last script. Just change the file name again. This one is a little bit further down. Change it to 1110 in this case, and then save and run. So this will just give you the final graph, which shows you the force and the deformation related to each other, and the final Young's modulus values for the different percentage points of the deformation throughout the movement of the air. So you can see E1 in this case is 10% deformation, E2 is 15%, and E3 is 20%. And then E23 is the average from the beginning of E2 to the end of the period represented by E3. And they should generally go up. If you don't use enough force sometimes on soft tissue, it will actually go down, but that shouldn't be a problem with this device, because as long as you make sure that you have your finger reasonably close to the end of the OCT so that the force can transmit, then you should get data that looks about like this. Now the range should also be sort of what you see here. This is a little bit low, so if you use a little bit more force, which you don't necessarily get to control, but generally the closer your finger is to the end of the OCT, the more force is transmitted from the air into the tissue. You should get some slightly higher readings. Now, one more note, you can see in here there's an array called ratio H3. This is what controls the percentage points throughout the overall growing and releasing of the air jet that represent the different Young's modulus values on the graph. So in this example, it's 10%, 15%, 20% deformation. We find the Young's modulus values. If you wanted to change that to like 5, 10, 15, then you would just change these in order. So I'll change this to 0.05, 0.1, and 0.15. And now if we run this again, it will show you some different Young's modulus values, because this is now at 5, 10, and 15% deformation, respectively, for E1, E2, and E3. Now, finally, once you're done, you can close out of MATLAB. Just go back to wherever it is that you're storing your project and go to the data save folder. And in here, you'll be able to find all of the JPEG files for the graphs that you just generated. So I'll organize by type, and all of the JPEGs are at the bottom. You see your stitched together image from the center columns, and then the tracked version, and then the deformation frame graphs, force frame graphs, and then the force deformation time graph and the hysteresis curves, all there. And then your final one with the Young's modulus values on it. Now the device takes program inputs in the form of CSV files that have time in milliseconds on the left and then motor position in degrees on the right. So to write a program for the device, all you have to do is open up something that can edit a CSV, like Excel or even Notepad, and just enter in the times. So I'm going to do a really quick example here. I'll just put in like whole second times, and I'll have it run for 10 seconds total. So because it's milliseconds, you have to remember to put the thousands at the end. And I usually like to give a buffer second in the beginning, so I'll do 0, 0 for the motor position at the beginning and 0, 0 at the end. Now in between, I'll have it running at 300 degrees per second, so I'll just do 300, 0, 300, 0, 300, 0, 300, 0. And so this will move the motor 4 times up and down to 300 degrees from 0. And so because those happen over intervals of 1 second, the speed is 300 degrees per second. The maximum speed that you can move the motor at is 400 degrees per second, which is 720 degrees per 1.8 seconds, which is what the default program does. So if you try to run it faster than that, it will potentially get too hot or draw too much current, probably skip steps, and the software will not let you run the motor at that speed anyway. So just be wary of that when you're writing the program. You'll know it won't damage the motor at all, but if you try to run a program that tries to move the motor faster than 400 degrees per second, it will just move too slowly because the software will restrict you. Now, when you want to save your program, just go to File, Save As, and I'll put it on the desktop and I'll just call it My Program. and make sure to change the file format to CSV and then save. So now I'll quit, and I have myprogram.csv on the desktop. On Mac, you can use preview with the spacebar just to check the contents, but that's exactly what we just wrote. To load the program, just take the SD card that goes into the Arduino, which is this, and put it into an SD card reader. If your laptop doesn't have an SD card slot, mine does not. And then plug it in, open it up, and you'll see an SD card with 3 folders on it. There's in, out, and SYS, and the SYS folder is just for the system, so it has the calibration data and the Wi-Fi credentials on it. So for loading programs, you put the program into the in folder. So we have default.csv and now myprogram.csv.